All right, let's look at reaction mechanisms and homogeneous catalysts. Now, reaction mechanism is a balanced chemical equation that provides information about the beginning and the end of the reaction, but the mechanism gives us a pathway. So a balanced reaction, like you've done up until this point, just tells us, hey, here's what's going on, here's the beginning, here's the end, this is what happened. The mechanism gives us a detailed picture of the middle. Mechanisms are divided into elementary steps, where an elementary step is a process that occurs in a single step. It can't be a multi-step thing or anything like that. The molecularity is essentially the reaction order of that elementary step, and it represents the number of molecules present. So a unimolecular, the one molecule in the elementary step, bimolecular, 2 molecules in the elementary step, and intermolecular, 3 molecules in the elementary step. The more molecules you have to get together at the same time, the less likely that is. Unimolecular is pretty common, bimolecular is very common, intermolecular is getting uncommon, and beyond that, it becomes increasingly uncommon, as you might imagine. So it's not common to see that because it's just not statistically likely. It happens, but rarely. Elementary steps must add to give the balanced chemical equation. The intermediates formed in the elementary steps have to cancel. That means it appears in the middle, but it's used up and is not a reactant or a product. And so unimolecular processes are first order, bimolecular processes are second order, intermolecular processes are third order. And just like reaction orders, that third order reaction with respect to something is uncommon. A lot of things are first and second. Elementary steps are directly related to stoichiometry, but the overall reaction need not be, and many times is not. One of the elementary steps will occur more slowly than the other steps, and we call that the rate determining step. And so fast steps that occur before that slower rate determining step impact the kinetics in terms of the order of the reaction. Ones that happen after that don't, which is why, as we said before, the stoichiometry does not determine the reaction order for the rate law. And so the rate law is determined from the mechanism, shows the reactants involved in the slow step only if it occurs first, or the slow step and any fast steps that precede it. And for you to have a proper mechanism, the orders of each reactant, once you're done with the mechanism, should match the experimentally determined reaction orders, or you don't really have a good mechanism. And so let's look at this. And so let's consider this mechanism where NO reacts with Br2 to form NOBr2 in equilibrium, and that's a fast step. And then we got NOBr2 plus NO going to form 2NOBr. That is a slow step or a rate determining step. So we want to know what the overall reaction is. Can we identify any intermediates, and what's the rate law? Intermediates are pretty easy. What cancels? It looks like that NOBr2 is the intermediate because it's going to cancel. So it's on the product side of the first equation and the reactant side of the second equation. Nothing else is like that, so NRBr2 is our intermediate. So let's switch to the paper and we'll work on actually writing the rest of it out, the overall reaction and the rate law. So if we look at this, let's remember we said that was our intermediate. These two are on the same side, so they're going to add. So 2NO gas, we're going to bring that down, Br2 in the gas phase, reacting to form 2NOBr in the gas phase. So that's easy enough. Let's look at the molecularity. So we identified the intermediates, NOBr2, and now we want the rate law for the reaction. So the rate law is going to be rate is equal to K times the concentration of NO and the concentration of Br2. Now we just need to decide what the exponents are going to be. I see two NOs going from the fast step to the slow step, so NO is going to be second order. One bromine, so bromine is going to be first order. So in this case, the rate law does match the coefficients, but it doesn't always. Okay, here's a second question. We want to consider a different mechanism, but we're going to do the same things. We got chlorine breaking apart to form two chlorine atoms, which is fast. A chlorine atom reacting with H2S to form HCl and HS, another fast step. And then HS reacting with Cl to form HCl and S, which is a slow step. So again, we want the overall reactions, we want to identify the intermediates, and we want to write the rate law. So the first reaction has two chlorine atoms as products, and you can see in the next two reactions, chlorine atoms are reactants, and so that would cancel out, so that would be an intermediate. And we also see the HS is a product in reaction 2, but a reactant in reaction 3, so that would cancel. So HS and the chlorine atom, not the Cl2, the chlorine atom, are the intermediates. So let's take a look at that on paper. And so the intermediates will cancel, the HS and the chlorine atoms. The rest of it will add together. And so we'll say Cl2 plus H2S goes to form, add those together, 2HCl plus sulfur. And so that would be our balanced reaction. Again, the chlorine atoms and the HS are intermediates. The rate law is going to be rate equals K, concentration of Cl2, concentration of H2S. Now we see CO2 is only mentioned once and H2S is mentioned once, so we'll leave that alone on the exponent. So birth, our first order, and that would be our rate law for that particular reaction. Okay, so let's talk about homogeneous catalysis. Homogeneous catalysis involves reactions in which the rate of reaction is increased by adding a catalyst that's in the same phase as the reactants. You can have heterogeneous reactant or catalysts like, say, a metal. They're not a reactant, they're not consumed, and you should get it all back at the end. So in the presence of the bromide ion, hydrogen peroxide decomposes quite rapidly, where it decomposes much more slowly under ordinary circumstances. So the bromide reacts with hydrogen peroxide and a little bit acidic solution. So we got the H plus in there, and we form bromine plus the water. The cool thing about this reaction is that you'll see that brown color appear and then disappear because bromine is brown and it is our intermediate. Bromine will then react with more hydrogen peroxide to produce the bromide, the acid, and the O2. So the bromide and the acid I get back at the end. So they're not consumed and would in fact cancel. And we would just get our basic decomposition reaction at the end. Catalysts usually operate by providing a mechanism where you can get an alternate pathway that is lower in energy. And that happens by lowering the activation energy for the reaction. And so if we look at that, we have an uncatalyzed reaction on the left versus a catalyzed reaction on the right. And we can see that we just have our nice uniform hump on the left like we normally would. But in the second one, we see that the hump is shorter and there's more than one peak. Usually that's because of the formation of one or more intermediates. So our overall activation energy is lower, so the reaction proceeds more quickly. And that's why a catalyst ends up working.